Well, we're going to make this installment number 5. This is Matt, your lovely daytime host. We're going to do a little bit of review about what we talked about last time, about the different types of logic gates that we reviewed. And then we're going to talk about math again and show you how these logic gates can come together and do something interesting, like, do some math, do some addition. So here we go. Let's talk about, again, the types of logic gates we have. The first one, we talked about, looks like this. This is an inverter. Sometimes you'll see it called a NOT gate because it just flips the input. If the input is a 0, the output is a 1. If the input's a 1, the output's a 0. Okay, the next one we have is the AND gate. These are at least 2 inputs. All right, this is called the AND. God, okay. I gotta learn to make better ends. All right, and again, that one, you know what, I'm gonna redraw that one because I think it looks terrible. The AND gate, if 2 inputs are 1, then the output is 1. All right. If you have a 4 input or a 5 input AND gate, if all the inputs are 1, then the output is 1. Any other combination, the output is 0. All right. They all have to be 1. Each one, the first and the second and the third, and however many inputs you have to be 1 for that output to be 1. The third one is the OR gate. Kind of looks like a Star Trek insignia. That is the OR. And remember, that can be anywhere from 2 inputs on up. And all it requires is that if one of the inputs is 1, then the output is 1. And the other way of thinking of it is if all the inputs are 0, that's how you get 0 at the output. Otherwise, you're going to get a 1. And then finally, the last one here is the XOR. Looks like the OR, but a little extra thingy-jig on the end. XOR. And that one requires that one of them is 1, the other one is 0. And that's how you get a 1 at the end. That's how you get a true, or a truth at the end, a 1. If both are 0 or both are 1 on the input, the output is 0. And again, these are your Lego blocks. These are what you can use to take over the world, at least in terms of building chips. You also remember that we talked about the variants that exist. So we have, as we have an AND gate, we also have something called a NAND gate. And we'll just review that really quick. A NAND gate kind of looks like an AND gate, but it's got a little circle on the end that reminds you of the inverter, actually. Reminds you of what that looks like, and it will invert the signal at the end. That is the same as if we drew an AND gate, and then we had an inverter. All right, that's the same thing. It does the same thing. Let me remove that part. So we've got, this is NAND. Again, just think of it as NOT along with the AND, or a inverted AND at the end. We have a NOR. We're going to draw that with a circle at the end. Again, excuse my terrible drawing. NOR, same thing. It's an OR with an inverter at the end. And then we have the XNOR, which is this with a circle there. Make a bigger circle. That is XNOR. That is, again, an XOR gate with an inverter after it, implied. So, with all of that said, we're going to jump into a little bit more here and talk about addition, right? Now, you remember that when we chatted before, we thought of these as operators when we were thinking in the math perspective, right? We said, well, we've got like with and. You can kind of draw it this way. We drew this first, actually. We said this is an and. We said there are two inputs for a two-input and there's one output, right? So these are the inputs, and this is the output here, right? And so we thought of the inputs on one side, output on the other. And yet when we write math equations, so let's take a simple one here. Let's say 7 plus 8. All right, we know that equals 15. In the land of math, we don't typically think of input and output so much, right? We just see 7 plus 8 equals 15, and well, there you go. But if you were to write this kind of in the notation that we're talking about with these gates above, or even this little box diagram that I created with inputs and outputs, you could kind of think of addition as doing the same kind of thing. Think of it as a box. This operator here is plus, or addition, right? And you've got two inputs, and you've got an output. In this case, the inputs are 7 and 8. And this little box here is going to do something. It's going to perform the addition, and the output is going to be 15, right? Now, let's go back and remember, I'm going to go through some very basic things here, but I want to talk through it. When we do addition, we kind of take it for granted, right? We do 7 and 8. We do a plus sign here. We kind of draw the line below, and we say, well, it's 15. But we're kind of going very quickly. Let's go back and actually see what we're doing. All right, we're doing two things. We're doing a 7 plus 8, and we're saying, okay, clearly we don't have enough digits in order to do this in one column, right? In one column here, we have 7 plus 8. If you're looking at the total number of digits you have between 0 and 9 in decimal, we don't have a single digit called 15. We have actually, 15 is made up of two digits. So we have this thing that happens where we take 7 plus 8 and we say, well, that turns into 15, but we actually are carrying a 1 over implied, all right? And that 1 drops down. Right, and we learned this when we were little kids, just learning how to do addition. But as we grew up, we just kind of forgot about it, and we do it in our heads all the time. Right. If I take something else like 23 and 9, right, same thing. 3 plus 9 is 12, but we can't write 12. Oops. We can't write 12 necessarily. We have to write the 2. Carry the 1, and then the 1 plus 2 is 3, and that's how we get the answer 32. So when we think about, I'm going to, actually let me erase this here for a moment. When we think about this little box that we drew before, you could say, very simplistically, yeah, the answer is 15, but in general, what happens when you have two inputs? You actually have two outputs. You have a sum and you have a carry. Right? Now, if you're talking about single digits, so imagine we're talking only digits between 0 and 9. So this little section here, this input can only be between 0 and 9. So maybe your number here is 9, maybe it's 4, or maybe it's 3, but it can't be 12. Right, because we're just saying that is a single digit representation. And this one here, right, this one can only be between 0 and 9, these inputs coming in. So you kind of, you can obviously see that if your input here is 9 and your input here is 0, you're going to get a sum of 9 and a carry of 0 because there's no carry, right? But if I come back here and say, well, my input is 7 and my other input here is 8, like we were talking about, now what is the sum? Well, the sum part is the 5, right, just like from over here, and the carry is 1, which is this part. So, you can tell and you can see quickly that when you have a inputs here of that are just 1 digit long and 1 digit long on each number. So this is the first number you can put in. This is the second number you can put in. And it can only be 1 digit between 0 and 9 and 0 and 9. Your output, you have to accommodate for the carry, right? Because it's possible these two numbers will add up to something greater than 9. And at that point, this is what you have. You have a sum of that is going to produce, the sum produced is 5, right? But the carry is 1, and that's what makes it 15. I know you have to kind of read it from bottom up the way I drew it, but that's exactly how it works. Okay, so let me go back and let's talk about this same thing in binary. Doop-a-doop-a-doop. Try to erase here. Oh, no, I got to erase everything. Okay. So let's talk about the same thing, but we're going to do it with binary numbers. So imagine that we are adding two numbers, and we're going to do it, again, using just zeros and ones. That's all we have. All right, so we've got the first number, which is, let's call that n, and let's call this m. No, let's not do that because I won't be able to say those right. Let's call this A and B, and we'll call this the sum and the carry. Right? So it's exactly what we showed before, except we're just saying that, you know what, these numbers here, this A can only be between 0 and 1, and this B can only be between 0 and 1, which really just means, when I say between 0 and 1, that means it can be either 0 or 1, right? There's no other, there's no 0.5, right? We're just talking integer digits here. So before I said between 0 and 9, so that could be all the way from 0 all the way up to 9, but here you only have 2 digits in binary. You only have 0 and 1. So how do we do this? And let's just run this out. Well, if I have a table, I'm going to draw a table. The nice thing is when you only have 2 digits, it makes the number of combinations quite small, right? So I've got I'll call two inputs here. I've got an A input and a B input. And now the outputs, what can they be? Well, they can be, there's a sum and there's a carry. And so what are all the possible combinations for the inputs? Well, I think you probably have seen this before. You can have 0, 0, 0, 1, 1, 0, and 1, 1. So let's add them up, because this sum is what? A plus B. So 0 plus 0 is 0. Great. Is there a carry? No. 0 plus 1. Well, 1. Is there a carry? No. 1 plus 0. What is that? 1. Is there a carry? No. Now, 1 plus 1. Now we have to go back and remember how to do this, all right? 1 plus 1 in binary is going to add up to 0 with a carry of 1. All right. Remember, these digits, what is 1? This is binary 1. This is, I'm sorry, decimal. This is the decimal version over here. We've got decimal version of 1, decimal 1. 1, 0 is a decimal version of 2. So 1 plus 1 is 2. It works out the same, again, as it should in decimal as it does in binary. So therefore, when we take these and say 1 plus 1, that's actually 0, isn't it? With a carry of 1. So what we've done is we put together, they call these truth tables. It's just a table of showing all possible combinations here of what can happen when you have 2 inputs on an adder, on this little adder that we made, this little operator that can do plus. All right, again, I'll draw it here. You got A and B. You've got the sum, and you've got the carry on the output. This is the outputs here, and these are the inputs here. So, great. If we look at this, though, and say, well, 2 inputs here, this signature, this 0110, boy, that looks familiar, doesn't it? Now let's go back and remember. Do you remember all the way up here, we talked about XOR, and we said, if the inputs are both 0, the output is 0. If the inputs are both 1, the output is 0. Only when you have one or the other. All right, so it could be a 1 here, or a 0 here, or a 0 here, and a 1 here. Only then is the output 1. Well, look, that's exactly what this does. This here is equivalent to what we call, and let me write this differently, is an XOR. All right, it is the XOR. Oh God, that is terrible. Let me try drawing that again. One day I will learn to draw better. That is an XOR of A and B, with the output being S. Great. Now look at this one over here on the carry. The carry, the only time the output is 1 is when the inputs are both 1. Boy, that looks like an AND, doesn't it? That's exactly what it is. So this one here is an AND. And so now we can take, and we just draw it this way, A and B, and there's the carry. So now we've just shown that we can use 2 logic gates and together produce both the sum and the carry. Excuse my dogs. So this is kind of cool, isn't it? And this is where I wanted to show you how the logic gates can be used together. And I'm not going to draw the whole diagram of how to do this in drawing the whole logic wire diagram out. But I wanted you to see that you can take these logic gates that we were using before and turn them into tools that can help you do something else, like add up 2 numbers. And it turns out that you can cascade these. So if you have your XORs and your ANDs, and if you do this in a certain way where the carry of 1 goes into the next block to do the addition for the next, you can effectively create a cascade where you can do any number of bits. So right now I was talking about 2-digit or 2-bit, each number is either a 0 or a 1 coming in. But what if you wanted to add a number that was 10 bits long or 10 digits long to another number that's 10 digits long? Well, you could use this same method and it all connects to each other, going from right to left, to produce now the ability to add 2 10-bit numbers together. And you just are using these XORs and these ANDs. And that's how you build things like adders. And you can go more complex. You can do adders. You can do, there's ways to do subtraction. And then there's other things that you can do, which I won't go into, which, multipliers and things like that. But I wanted to show you that these gates, these things that I've been talking about, these logical operations, now allow you to do things in the computer as you use day to day, right? You go on a computer and it adds things together. It's using adders, and these adders are constructed from these little Lego blocks of gates. And this we just demonstrated here. This is one way to do it. So with that said, I think I'm going to wrap up. I hope you enjoyed it. This little trip down the path of logic to math. And next time we'll talk about something a little different. You have a good day. Goodbye.